guess, does anybody have any more questions for our guest, Doug Hessig? Any questions?
Yeah.
Are there any grad students here?
Yeah, several.
What? Several, yeah.
So I am completely happy with, if you haven't seen any of this stuff before, very basic questions too. I'm very happy to answer those. Like, we talked a lot about L functions, the zeta functions, and I bet you may or may have not seen those before.
Yeah. And one of them is Lin, yeah, she's my graduate student, and we were talking about Kusuman sum this morning.
Ah, because
yeah,
they pop up everywhere.
Right.
Work on another type of exponential sum. So yeah, I was writing my research statement, and I want to mention about Kusuman sum is actually a special case in this character sum that I was working on.
Mm. Yeah, that I mean, so this is the work I presented here was, just focus on these two families. The Klusterman sums is also hyperklusterman sums and other families too. And I've work with Steven Sperber have looked at symmetric powers of all types of families, but in terms of automorphic interpretations of these things, I'm still trying to get my feel for how, like, what to expect and how they should look and so forth. So this is kind of still, and so that interpretation is, I still feel like it's budding. Yeah, it's still, yeah. And people do have other results on these things, not exactly like this, but in terms of some other representation theory and interpretations.
Well, one thing that's very different about the Klusterman sums is they don't immediately connect to algebraic varieties. You can view them from many angles. I mean, there's also the point of view of differential equations, as you mentioned. The differential equation satisfied by the Klusterman sum, so to speak, the analog of it is a confluent hypergeometric.
That's right.
And they don't correspond to any family of algebraic varieties, because it's a theorem that when you have a family of algebraic varieties, the Picard-Fuchs is regular singular.
That's right.
So you're stymied right there. So there's no, as we would say, motivic interpretation, at least no obvious motivic interpretation of these Klusterman sums. When I was in China last summer, not this last summer, a year ago summer, I met some of these people, Zhang Daoyu and Fu, Lei Fu, and these people. And, they have all kinds of exciting new results about these Klusterman sums and their L functions. But it's a brave new world because you're outside the usual game where you relate these things to motives, you see.
Yep.
And so people have tried to generalize the theory of motives. They have the things they call exponential motives.
Right.
They have things called irregular Hodge theory, and Zheng Daoyu and others have worked on this, But it's a whole brave new world. I mean, people are just trying to feel around for what the results would even be like. And, definitely working out concrete cases where you can say something is definitely interesting.
Yeah. I was kind of surprised with the p is equal to 2 and 3 that they worked out as it did, in some sense, that because as you say, that the Bessel differential equation is this confluent thing, but there is this relationship with elliptic curves that just happens to be for p is equal to 2 and 3, and it's right, and that same trick doesn't work for the larger ones, for larger primes, and so it's not clear. It's not. I don't know. It's not clear.
One thing I do remember from that talk, this was a talk that was given in the summer of 2019 in Beijing. This was a talk that I believe Zheng Daoyu gave. And, you know, he was talking about, I think you mentioned Yu and Sabah and
Yeah,
Fuzan.
yeah.
And he was talking about those results. And somebody asked him a question about the connection to motives. And he, frankly, I didn't understand his reply, but it had something like this. It says, well, in fact, we can relate these to classical motives in some way. And I have no clue what that meant. So if you know what paper I'm talking about, it's a great big, he's, you know, Yu and Sabah and what are the, Frizan,
Right.
one or two of those papers where they talk about the L functions of these Klusterman sums. And they prove, now they're not looking p-adically, but they put together a global L function, you know, for all the primes. So this is, you know, you're really concentrating on one prime at a time, right?
Right. Yeah, they look at all of them. That's right.
Right, take a global L function. And they prove some wonderful results about special values of this L function, which I understand the physicist of all people had discovered experimentally. Don't ask me.
Really? I didn't know
But
that.
they're related to what you call periods of Bessel functions. Now, this is brave new world. You know, we know about periods of integrals of algebraic functions.
Right.
And we're familiar with the idea that these periods often appear as special values of L functions of, you know, algebraic varieties. That's sort of, maybe not everybody knows it, but it's semi-familiar. But the physicists had been looking experimentally at these things, and I think they discovered certain kinds of integrals of Bessel functions, which are now interpreted as quote unquote periods of these irregular connections. So we're talking about, so there is a notion of periods of Bessel functions. Okay, whole new world. It's a whole new world. And I have often told myself that if I were a young man and vigorous and everything, I would go and learn all that stuff, because I think this is some of the really exciting stuff that's happening.
Yeah.
But anyway,
Yeah, JD told me he's so I have some old work that I looked at exponential sums of this cubic x cubed plus t times x.
yeah.
And there you get the Airy differential equation. It's a
Wow.
And but then the symmetric powers are complicated because you have these Gauss sums that pop up and so forth. So it's a little bit tricky. And he told me that they are trying to do that now. Look at this Airy family.
The same game.
Same game, but for the Airy family, because it's more complicated, because it depends now. You have these different characters come in, and they don't know how it's going to happen when these different characters, come in. Yeah, I don't know what they're doing with that, but
They being you and Sabah and those.
right.
Yeah.
Yep.
Well, I think this is really a brave new world. You know, whole new things come up on all, you know, in all viewpoints. I mean, even in Hodge theory, it's a whole new game. You know, people understood motives or mixed Hodge structures and all this other stuff, but this thing jumps right outside the box. These things are not mixed Hodge structures. They're something new.
Yeah.
And yet they seem to have periods which are meaningful, and they seem to be involved with L functions.
Yep. Yeah.
But there isn't an obvious cohomology. I mean, you have this Dwork theory, as you point out. It's a kind of cohomology theory.
Right.
But what algebraic variety does it relate to? I mean, it doesn't seem to relate to any algebraic variety at all.
No, exactly. Because I mean, it can't directly, right? As you pointed out, you have the regular singular points versus irregular, and so it can't be direct. But I don't know. Like I don't. Yeah. It's one of the reasons I find this work exciting. This field, because it's I think it borders on a lot of stuff that's known, but all but then don't quite know what to expect. It's fun.
Do you know that Ron Evans makes some conjectures on up to seventh moment, right? I think looks like relating to what you are doing over here. There is some modular form pop up.
Yeah, so he seems to kind of go in a slightly different, I mean, it is, but it's slightly different direction, but he does it, he likes formulas that where you fix the weight K, and then you want a formula for all P. And I fix the prime P, and I want a formula for
Okay,
all K. Yeah, and so it's slightly different, different formulas. I mean, math is unified. I'm sure there's ways to connect these, you know, what we're doing. But his, I've looked for his work for it to help me guess at what would happen when P is equal to 5 or more, because that he, you know, he has stuff on that because he fixes the K. It has prime be whatever. But I don't know what happens when P is 5 or more. Yeah. I don't know. Actually, hey, I'm going to throw something really weird at you guys. So I hadn't actually thought about doing this, but since I'll bend your ear. All right. So, all right, you brought this up. Is pi squared is Dwork's pi. Pi squared. Okay, I just want to note that when P is 2, this pi is equal to 2, and you get 4 right here. All right. When P is equal to 3, pi is square root of 3, and this becomes 3. So when P is 2, this is 4. When P is 3, this is 3. Right? There might be a minus sign in there too. I don't know. But here's this formula. When P is equal to 2, gamma 1 of 4 is right here. This is pi squared. When P is equal to 3, this is gamma 1 of 3. This is pi squared right here. When P is equal to 5, this should be gamma 1 of pi squared for 5. But when P is 5, I mean, pi squared of 5, sorry, pi squared when P is equal to 5 is not, it's a real number.
Yeah.
It's not an integer. And I don't know what cusp forms are. I mean, I don't know what congruent subgroups are when this is not an integer. I don't know that theory well enough to say, you know, what to even hazard a guess. But I found, this 4 and this 3 are it's not a coincidence that these are basically pi squared. But I don't, and again, I don't know what happens when P is equal to 5, but the numerology suggests that, you know, looking at gamma 1 of pi squared, I don't know what that is. I don't know. But anyway, throwing it out there.
Well, Hita has these modular forms like this, but I don't know about it either.
There is something called a Hecka group.
Hecka group, right.
Yeah. And then the H5 probably contains square root 5.
And that might be what I'm looking for here. I don't know. So it was this stuff right here. This P is equal to 2 and P is equal to 3. This is like 4 weeks ago. I came up with this. I had some time and out it popped. I got kind of lucky, but I haven't done too much since school started.
Yeah, very nice talk. Thank you.
Thank you very much.
Thank you guys. Thank you.
Any other questions from the students? All right.
Bye.
Yeah. Okay, Dom, maybe I send you a separate email. We have something which is kind of related to what you're talking.
Okay, great. Yeah, we can talk more then.
All right. Thank you.
All right. Well, have a good night, everyone.
All right. Thank
Bye,
you.
everyone.
Goodbye.
Bye-bye.